All right, suggestions. Let's just talk through the process here. What do I need to do? Let's kind of try to get into a pattern. What should I probably do first? I can't. Probably just do the domain first, how about? And then we can look at end behavior if we want, okay? So what's the domain here? How are we going to figure this out?
Be positive or negative.
Okay, how'd you get that?
Because it's either those and it's 0 on the bottom.
Okay, so we got to find, we have to disallow any places where we have zeros of the denominator, right? Bottom would equal 0 when x squared is 1. That's going to be plus or minus 1, right? So we'll just say it that way, okay? All right, so that's good. End behavior, should we go ahead and do end behavior? Okay, which kind of, are we going to get a horizontal asymptote here if we take limits? We're not, correct. Okay, but what's interesting about the end behavior? We're going to get slant asymptote. How do you know? Okay, good. The top is 1 degree larger than the bottom, right? So when I divide these out, I know I'm going to get a linear, a linear equation plus some remainder, right? So let's go ahead and divide this out. Let me go to another page for that. And let's talk about our options for dividing this out. If I want to simplify this quotient, talk to me about that. What are my options? I could divide it using long division, right? And it'd be a pretty easy one to do that way. Let's just zip through one of those where we don't have any. This will be an easier one. Last one we did had fractions. This one won't have any fractions. How's that look? So I've got my, I don't even know what you call that thing. I don't know what it is. The little division doohickey. So what goes where? Inside, because the numerator goes inside, denominator goes outside. Remember, the denominator, we don't have to hold every value of x in the denominator, but inside we do, right? So how do I need to write the polynomial inside?
0 squared.
Yeah, good. Plus 0x squared plus 0x plus 0. And then leading term outside divides into leading term inside how many times? X squared times what is x cubed? X. Okay. So we'll distribute, and I get x cubed minus x. Now you can see the value of having those columns, right? So the x's line up. Okay. And then we're going to, and I urge you to do this every time. Just get in a habit. So we're going to put that in parentheses and put a negative out front. So we know we're going to distribute the negative all the way through. X cubed minus x cubed, of course, cancels. 0 I don't need to worry about. And 0 minus negative 1x is x, right? Plus 0. And then we're done after one step, aren't we? Because x squared won't divide into x evenly, right? So what's our answer then? So this is equal to?
X plus x with x.
Okay, good. So here's, this is part of the polynomial part of our answer on top, right? So we're going to get an x plus, and then this is the remainder, right? So we're going to get plus x divided by my denominator. That's what remains over the denominator, right? Okay, what would have been another way to do that one? This one worked out really quickly, but long division sometimes can be a little tedious. Can I use synthetic division directly on this one? I can't. But because the bottom is not linear, right? But what if we let's just try this whole thing again here real quick. Look at a shortcut maybe. Here's something that sometimes is a good idea. Does the bottom factor easily?
X plus 4 times x minus.
Good, so it's a difference of squares, isn't it? So it's going to be that conjugate pattern. So we get x cubed over x plus 1 times x minus 1, right? So can you think of a strategy for using synthetic division, which is easy now? I've got two factors on the bottom. What if let's take numbers. What if I had something like 24 divided by 6, and we're saying, okay, well, 6 is really breaks into the factors 2 and 3. How could I do this in 2 steps?
4 divided by 2 divided by 3.
Yeah, 24 divided by 2 is what?
12.
Divided by 3 is?
12.
Okay, 24 over 6 is 4. You get the idea, right? So we could do this in small, easy steps, right, that are synthetic division steps. So let's write this out as a synthetic division template. Okay, probably a good thing to review anyway, I'm guessing. So if we want to write this out using synthetic division, remember how that works? Is this how you guys did it? You wrote the bar like that?
Yeah.
Okay. And then if you do it this way, that's fine. This is a good way to do it. Then you always need to put a remainder box down there. You got to put a box because otherwise you'll forget to do something important there. Now, what goes where? Let's say we're going to divide this one. Let's divide this one first. Okay, so the x plus 1 is the denominator. What goes out front? So that's telling me, I'm just seeing if you can remember this. So if I wanted, but I'm not going to put, no variables will show up in here, right? It's just a bunch of numbers. So what number goes out there and why? Not 1. -1. How come? The 0. Good. We want to put the 0 of the factor, right? So that goes out front, right? The 0 of the denominator goes out front, and then what goes up here? That's the coefficient row, right? So I got a 1, but I can't just put a 1. It's got to be 1, 0, 0, 0, right? Because I have to maintain a column for every power of x, all the way down to the constant, right? Okay, so what do we get here if we do this? This may or may not work great, but we'll try it. So if I bring down the 1, what happens? Okay, -1 times 1 is -1. Okay, and then we add synthetically, right? We do the opposite of long division. So we add, we get a -1. -1 times 1 is 1, plus 0 is 1. And then -1 times 1 is -1. And if I add these, I get a remainder of -1. So what does this equal then? So if I divide the whole thing, if I divide x cubed by x plus 1, then that's telling me that I get a remainder of -1. This is going to be the new constant, coefficient of x squared, right? So in this case, it's probably not going to end up being that helpful, right? So now we get this part right here becomes x squared minus x plus 1 minus 1 over x plus 1. But we still have to multiply through by 1 over x minus 1, right? Because we haven't done this part yet, right? So we got to take this whole thing and divide it all by x minus 1, right? Okay, so how's that going to look? Well, we could break this into a couple parts. This part's no big deal, right? That's just going to give, I can divide that synthetically again, right? So I'm going to get the easily divided part. And then what is 1 over, what I end up over here with is minus 1 over,
What just happened?
say it again.
For that salmon colored?
So I'm just saying that everything, let me kind of do this. So everything in there is right there, right? I didn't do anything special. I didn't change anything. I'm just gonna break it into a couple parts. I've got a polynomial divided, I got a rational function part, and then I've got this part over here that's already got a denominator that I'm going to multiply through by 1 over x minus 1. Effectively, all I did was I just distributed the 1 over x minus 1 to the polynomial part and the remainder part. Right? Does that make sense? Okay, so this part we can deal with synthetically. This isn't a big deal either, though. I'm just multiplying fractions, essentially, right? Rational functions. What does this become?
1 over x squared minus
1 over x squared minus 1, right? So we get minus 1 over x squared minus 1, and then what's this? Well, we'll find out. We'll divide through synthetically. But look what you can do. This is kind of cool. Notice that where did we get the polynomial part? It's from these coefficients, isn't it? Right? So let's just nest our synthetic division, and we'll just do this process again, right there. See what I'm saying? Right? Because these are the coefficients that are giving us this polynomial, right? And now what's the number that's going to go out in front this time? Yeah, positive 1, because we're dividing it by x minus 1, so that's going to give us a positive 1 out front, right? And let's see what happens with that. If I bring down the 1, 1 times 1 is 1, plus negative 1 is 0, 1 times 0 is 0, add those up and I get 1. Right, so what's the result of all that then? Everything over here that's in this green box is just going to become x squared, right, plus, or sorry, x, not x squared, x, because that's our constant, x plus 0 plus 1 over x minus 1, right? Okay? Okay. Well, okay, so our answer then is just going to be, oh, sorry, hang on, what did I, now the green box is in the wrong spot. Green box is, oh, that's not going to work, I just got to erase it. I put the green box and I got to fix that, because that's going to mess you up. Where should the green box have gone?
On the purple one.
Yeah, good. Let's make it, we'll make it not green, we'll make it orange. There, everything there just became that, right? Okay, and so then we just end up with this minus 1 over x squared minus 1, right? So our final answer then just looks like x plus 1 over x minus 1 minus 1 over x squared minus 1, right?
Wait, then how do you get an x on top?
Say it again.
Like,
How do I get an x on the top?
oh, we did the other way. Yeah.
How did that?
On the top right here?
Yeah.
Well, because what we did here is we just divided it out using long division,
I know,
right?
but in the remainder.
In the remainder, okay, so you notice something then. Look at this. This is pretty cool. So everything here, right, has to equal that. And it does. And that's actually something we're going to, I don't know if we'll get to this. This is probably be pretty ambitious for a first year high school calculus class to get to the method of partial fractions, but you'll do this next year in college. When you're trying to learn how to do the opposite of differentiation, when you're learning how to integrate, when you're integrating functions like this, one of the things you're going to do is you're going to break down a rational function into partial fractions. And so we would start with this, and then we'll break that down into the sum of those two easier partial fractions. Okay. For us though, think about this. If we're just trying to find end behavior, does it make any difference? If I'm taking a limit as x goes to infinity, what happens to both of those?
0.
Go to 0. What happens to,
How did the x squared minus 1 get on the bottom? It would make sense if there was the x minus 1, you scroll up a little tiny bit, in the salmon colored, since it's the minus 1 over x plus 1 divided by x minus 1, when you multiply by the reciprocal, why does that just kind of combine and become x squared minus 1? I understand that if you multiply it through, that's what you would get, x minus 1 times x plus 1, but wouldn't you multiply by the reciprocal?
You did. You multiplied by the reciprocal of x minus 1, which is 1 over x minus 1. Right? Because the x minus 1, what you've really got there is just a 1 over x minus 1, right?
Yeah.
See what I'm saying?
Yep.
And so, in this case, I mean, this didn't end up being super easy, but I want you to see something. In some cases it will. It'll be easier. But what I want you to see here is that if you had some big ugly polynomial that you didn't want to divide out, but you knew that the bottom was factorable, you could break it up into pieces like this, right? Because look at the, and this is I don't think I've ever showed this to a calculus class before, but this is, theoretically, this is kind of a cool approach to this. You know that if you're looking at end behavior, all of the rational functions where the bottom is higher order, you could just, who cares, you're just going to do away with them, right? Because you're taking the limit as x goes to infinity. So that's just a bunch of garbage that you can dump every time, right? All you care about is the polynomial part that's left over, right? So if we, hindsight's 20/20, if we went back through this process again, would we even really have to calculate what this is? No, because we know that it's going to go to 0, right? So all we really had to do when we went through the synthetic process was nest the synthetic division and just forget about that part, right? And then just keep going. Like once we divided the -1 in and we got our polynomial part of the answer, we'll just use the other factor of the denominator, right? Because remember, our denominator split up into x plus 1 and x minus 1, right? Right, so we can then divide through again. Well, here's where it was right here, where we broke it up. So first we divided the -1 in. We got the polynomial part of our answer. Forget about the remainder part. It's going to go to 0. Then whatever the leftover polynomial part is, we'll divide again synthetically, right? And all we really care about in our answer is that part. The remainder parts in the limit, in the infinite limit, are always going to go to 0.
So x is the only thing that matters.
Yeah. Yeah.
All right.
I mean, did you kind of get a glimmer of where that, I mean, this is way above and beyond the scope of a regular high school, you'll never see this in a high school calculus book, but it's, you see how you could use that to your benefit? I mean, it would be a lot easier if we had like a 7th degree polynomial that we're trying on the top that we're trying to divide through using long division. That's going to be a mess. I mean, that's going to be a page-long polynomial long division problem where you might make a mistake because there's so much writing to do, right? But if you just go through and do this little synthetic process, what if the bottom's only a cubic that's factorable? You could just nest this 3 times, and all you worry about is the part that's outside of the boxes at the end.
So what would you say the answer is to this equation?
So the answer to this equation is, okay, so in the limit, right, so now let's get back to what does this tell us? Either way you do it, we end up with something like that, right? Okay, well, what's our whole point here? We were trying to find end behavior, right? So if we're going to take the limit of this, what's going to happen? If I take the limit of f of x as x approaches plus or minus infinity, we get the limit of this answer, right? Of x plus x over x squared plus 1 as x approaches plus or minus infinity. Well, that one goes to 0, right? So as x goes to plus or minus infinity. And so what our function looks like is the line y equals x. That's our slant asymptote. Okay? So that's the whole point of this is, when we divide this out and we evaluate the limit so that the rational function at the end goes to 0, whatever we're left with, and there might have been, in some other cases, that might have been like an x minus 3, or a 2/3 x plus 7, or whatever, right? It's just going to look like the equation of a line plus some remainder that goes to 0, right? And so that gives us, if we go back to our, way back to this, our problem that we're working on 3 pages ago, this is just telling us that we have a slant asymptote along the line y equals x. Okay, and that'll show up in our table. Okay? Make sense?
Yes.
Okay, so there. Now finally we can get on to the calculus, right? And you don't have to, you don't have to do that trick. You can just divide this out using long division, right? That's fine. You don't, I mean, I'd urge you to try that once or twice, just so you can file it away for later use in future years, but you don't have to do it now. Okay, what about this? What's the next step then? Now we just got to make our table. We're going kind of back to stuff we're more familiar with. If we want to find extrema, what do we have to do? We got to differentiate. So let's take first derivative. How am I going to differentiate this? Okay, so I got low D high minus high D low. That's not how I remember it. I remember it as, if you write this as U over V, it's VDU minus UDV. I always remember it sounds like video. That's how I remember it. I always go VDU is the first term minus UDV, but VDU sounds like video. So that's my little mnemonic device that I'll never forget. But you could probably find a better one. If you like the low D high minus high D low, that's fine. But I always mix them up. I can't remember which one's which. So either way you slice it here, we get bottom times derivative of the top. What's the derivative of the top? Okay, keep going.
Minus x to the third times 2x.
Good, good. All divided by? Okay, good. So if we simplify, what are we going to get here? I could factor out an x squared, couldn't I? Right, on the top. So if I take out an x squared, what am I going to be left with? So that's going to go away, and I'm going to end up with just an x over here. So I get 3x squared minus 3 minus 2x squared, right? Which is going to reduce to what? And on the bottom, I just get my x squared minus 1 squared. What do I get on the top? Did I do all that right? I think so. I did.
X squared minus 3.
X squared minus 3, because I get 3x squared minus 2x squared, they combine. So my first derivative then, in simplified form, just looks like, in factored form, looks like x squared times x squared minus 3 over x squared minus 1 squared. Okay? All right, so there's first derivative. Second derivative is not going to be very fun. Second derivative, while we're at it here, we need to know concavity. So what's that going to be? Let's just leave it like that when we're doing it too. We could distribute the x squared if we want. Maybe we will. That's going to be a little bit messy if we have to do a product rule derivative whenever we differentiate the top, right? So let's go ahead and also just distribute the x squared. We'll have it in factored form here though too already, so when we find the zeros, that'll make it easy. If I distribute the x squared, I get x to the 4th minus 3x squared over x squared minus 1 quantity squared. Okay, so now, quotient rule again. What am I going to get?
X squared minus 1 squared.
Good, x squared minus 1 squared times
4x to the third.
Okay, everybody good? Okay, minus,
X to the fourth minus 3x squared times 2 times x squared times 2
times what?
That's it.
times 2
Two,
2x
2x, good. Okay. Now on the bottom, we just get, if I square this, I just get hand to the fourth, right? Okay, does this part over here make sense? Everybody following how we got this, the second term on the top? Okay. Now, one thing that might be useful here is that we remember we already had x to the fourth minus 3x squared is just this, isn't it? Right? We already had it factored over here, so if I want to replace that with an x squared times x squared minus 3, that might be useful, right? And then what about right here? What can I factor out of that?
2x
2x, so I could replace that with 2x times
2x squared minus 3.
Okay. That may or may not end up being real useful.
Cancel out x squared minus 1.
Yeah, it'll allow me, I can take a 2x out of this thing, couldn't I? Right. So now we got this big mess here. Let's factor out as much as we can from the top. So what can we take out of the top here?
X squared minus 1.
Oh, here. Let's do that. Okay, there we go. Okay, so I could factor out of the top, I could take out an x squared minus 1 to the 1, couldn't I? Right? And so that's going to cancel that out, and it'll cancel one of those, right? I could take out a 2x, it looks like. Okay, which cancels that, cancels that. What else? That's about it, isn't it? I think so. No other common factors. What if I take out an x squared? No, it's not going to help me much, is it? Well, no,
You get.
I guess we're stuck. No, I already did, right there. I got an x squared minus 2. I think we're stuck with that then, aren't we? So what I get from the first term, I'm left with an x squared minus 1. Okay, x squared minus 1 times 2x squared minus 3 minus what's left over here? It looks like a 2. And then that whole thing, right? Nothing up there canceled, right? So 2 times, we'll just go back to that form. Okay, all divided by x squared minus 1 to the 4th. But what's one thing I could do to make life a little bit easier?
Cancel that.
Okay, good. I could cancel out. I could cancel out an x squared minus 1, right? And then, what's that give me if I clean that up a little bit more? So that's gone, so I've got a 2x out front, and then this whole mess, right? So what's that going to become? If I multiply this all out, I'm going to get 2x cubed minus 3x squared minus 2x squared plus 3. So all that stuff just becomes that, right? That trinomial. Let's distribute the negative 2 minus, did I do that right? Oh, that's a 4. There we go. then minus 2x to the fourth, that's good, plus 6x squared, all divided by x squared minus 1 cubed. And then I get some good cancellation. Those go away. And then 6x squared minus 5x squared is just x squared plus 3. What's left on top? All divided by x squared minus 1 cubed. So there's our second derivative. Okay? You can see now maybe, I was not lying probably, you can now agree, at the beginning of the year when I said you will do as much algebra in this class as you've done cumulatively in your whole lives, probably way more actually. I mean, there's a lot of algebra involved in this. So let's find critical numbers. If here's our first derivative, we've got it factored right here. Let's find the zeros of the first derivative. Let's grab this and go to another page. First derivative, and there's second derivative. Okay, where are critical numbers in the first derivative going to be? Do we get any where it's undefined? The bottom equals 0 at plus or minus 1. Are those critical numbers?
No.
They're not. How come? You're right. They're not. Why not? They're not in the domain. Right. Okay. So we only need to find zeros at the top, right? So f prime equals 0 when x squared times x squared minus 3 equals 0. So what values are those going to be? X equals, what are the zeros that we have this factor? So let's apply the zero product property. What are the zeros of that factor? 0. How about this one? Plus or minus square root of 3. Okay, so those are all our first derivative critical numbers. What about the second derivative? And once again, same issue on the bottom. The bottom's undefined, where the function's undefined. But remember what we said yesterday, the derivatives inherit all the points of where the function's undefined, right? Those get handed down from generation to generation. So f double prime equals 0 when what?
When x is 0.
Yeah. When x equals 0. What about that one? Can it give us any zeros?
The same as.
No, not real zeros, right? Okay. So we only get one real 0 there. So now we can finally make our table. Say it again, question? Why doesn't this one give us zeros?
Yeah.
Because if I said x squared plus 3 equal to 0 and solve, I get x squared equals negative 3. So I'm going to get i's in it, right? And they wouldn't be real.
Is it a math god thing that the numerator of the second derivative looks very similar to the numerator of the first derivative? So look at, you have 2x times x squared plus 3 as opposed to x squared times x squared minus 3.
Kind of. It's a symmetry thing. Yeah. I mean, that's not always going to happen, but it did happen for a reason here. I mean, the fact that that 3 showed up in both places is probably not accidental. Yeah. So kind of a math god thing. Yeah. All right, so let's make our tables. so our domain went from negative infinity up to infinity, but there were some points in the middle where the function was undefined, right? We said at -1 and +1, the function was undefined, and let's go look at the original function for a second. How is it undefined? Are plus and minus 1, what's going on there?
Zero.
Zeros at the bottom, are they zeros at the top? So then what's that tell us? Vertical asymptote, good. Okay, so we can add, okay, vertical asymptotes there. We had a 0 ended up being a critical number of the first and second derivative, right? So that one, what happens there? Well, the jury's still out. We don't know yet. Right? It could be one, either it's going to be a point of inflection or it's going to be an extremum. We don't know yet. We had critical numbers for the first derivative at plus or minus radical 3, and that's going to be, those are numbers that are bigger than 1, right? So we could do positive √3 minus √3 there. What about our limits of our function? There's our function. As x approaches infinity, is this going to, what's the end behavior going to be? Is it going to be positive or negative infinity?
Positive.
Positive, because it's the slant asymptote y = x, right? So we could do this. We could say limit is minus infinity, limit positive infinity. And there really isn't a place on the table to show the slant asymptote. So that's something that we always just kind of tack on to the bottom. We'd say there's a slant asymptote y = x, right? Now, what about figuring out what's going on here? Talk to me about our strategy. Where am I going to test points? Negative square root of 3, we're going to test in row, bottom row, aren't we? Right? We'll look at the sign of the second derivative at negative radical 3. What are we going to get? We're going to get negative times positive, okay? So we get negative on the top. What about the bottom? Positive, right? Hold it. That's right, yeah, positive, right? So we get negative over positive is negative. So what's going on there? We got a horizontal asymptote. Yeah, it's a maximum, isn't it? Right? Okay, what about over here? If we try positive √3, these two terms are both going to be positive, and so is that one, isn't it? Right? So it's going to be positive. So what's that tell us? Minimum. Okay. If we look at our original function again, does it have symmetry? Doesn't, does it? Right? It doesn't have odd or even symmetry because we've got a mixture of the top being, the top is an x cubed, actually hang on. Top is odd, bottom is even, right? So that's actually not going to work. Because you can't have a mixture of, I don't think you can have a mixture of both, even in a rational function. In a polynomial, you can't, right? If we had a polynomial that had even and odd exponents, it would be neither, right? On this one, I gotta think. I don't think it will. I think you have to have the same rule for a rational function. I think. We'll see. I can't remember. Honestly, I can't remember. I can't think that hard right now. What's the other thing? So we resolve these. What's the one last thing we got to do? We may not finish it today, but what's the one last thing we got to do? We don't know what's going on here. Okay, what's our strategy going to be there? Think about it. You got it? What are we going to do? Test points where, probably? Okay, good. So we're going to have to pick points in there to test to see what's going on here, right? Okay. Well, we almost made it through one example in a whole period.